Okay, so I apologize that I couldn't see you on Wednesday afternoon. I got pulled into doing something in school at the last minute. Didn't realize on Tuesday when I saw you that it was going to happen. So hopefully the bookwork was okay and that you managed to get your way through it. You won't have done anywhere near all of it, I wouldn't have thought, but we've got time to have another go at that in the future if we need to. What I would say is that although I'm not going to be posting you explicit homework to do, I am going to try and leave you with things that you can be doing so that you've always got something to fall back on in a bored moment, or if you just want to push yourself forward a little bit more, maybe if you're thinking of doing an A-level in physics next year, you might want to just keep things topped up as much as you can. So that chapter 13 that I posted, there should be loads of that in there that will keep you going for a little while if you need it. Okay, so we're actually nudging towards the end of the waves topic. If you remember that we began on generic waves and we had a look at water waves and waves on a string and waves on a spring, and then we moved on to sound waves, and then now we're on these electromagnetic waves, and we've had a good look at most of the spectrum, including light waves when you did the reflection and the refraction. We're just going to focus on one more aspect of the spectrum today, infrared radiation. And then next week, we'll move on to the last little mini topic that's in this waves. And then we'll be done from the waves topic. So I reckon maybe another week and a half, and that'll be the waves topic done. Ordinarily, that would mean a test. I don't know whether to give you a test while you're at home or not. I don't know how that would go. I'm going to have a think about it and talk to the other physics teachers, maybe see whatever we choose to do, we'll do for everyone rather than just one class. So I'll let you know about that. We'll see. I'll give you something anyway. And then after that, there's only one more topic left, and it'll be just consolidating and assessing after that. So we are reaching the end. It's come around a lot quicker simply because we haven't been doing the practical work, and then we lost the month of mock exams. Yeah, that's the future, but let's get on with this today. So the reason that we're going to focus on infrared radiation is because, as we spoke about on Tuesday's lesson, the interaction between electromagnetic waves and matter is often one about scale and size. So lots and lots and lots of electromagnetic waves interact with the atom itself. We spoke about the electron transitions, and you might remember from nuclear physics that gamma rays are actually produced by the nucleus because they've got a wavelength of about 10 to the minus 15 meters, and the nucleus has got a size of about 10 to the minus 15 meters. X-rays and visible light and ultraviolet, they're all produced by the atom itself through electron transitions. But then we also spoke about the fact at the other end of the spectrum, you had the microwaves and the radio waves. And rather than being atom-sized, they were much, much bigger, meters and upwards, or centimeters and upwards. And that was much more to do with the motion of electrons over centimeters or meters or even kilometers. And so the size of the wavelength determines the size of the object that it interacts with. And nestling kind of in the middle between the radio waves and the microwaves and the ultraviolet X-rays and gamma rays and the visible lights, nestling in between there is the infrared. And we haven't really spoken about that yet. And the infrared has a wavelength such that it pretty much interacts with whole scale atoms and molecules. So not individual electrons within an atom, but the entire atom itself. Infrared tends to be produced when entire atoms vibrate around. And flipping that around, infrared waves often get absorbed by entire atoms. Not so much the electrons in the atoms, but the entire atom vibrates when it absorbs infrared. This is why we experience infrared as heat on our skin, because it makes the actual molecules in our skin and in our nerves vibrate around. And we experience that as a sensation because it's operating at the scale length of our nerve endings. If we were to be exposed to X-rays or gamma rays, it'll still interact with our body cells, but at a much smaller scale that doesn't stimulate the nerves. And so we could be exposed to X-rays and not feel any pain, even if it is interacting with our body. Likewise, when we are exposed to radio waves, they tend to go straight through us because we don't have anything within our body that is kind of meter-sized. And so there's nothing in our body to interact with a radio wave. But there is for infrared. Every cell in our body is capable of interacting with infrared waves because of their wavelength roughly matching the same kind of size scale. And so our entire body is an infrared detector. It detects the infrared as the sensation of warmth, of heat. Too much of it, painful heat. Also, all objects tend to emit it because, as we discussed back at the start of year 10, all objects have particles that are vibrating, and that vibrating motion tends to cause the emission of infrared radiation. So every single object in existence, just by being, tends to radiate infrared. We're all little infrared light bulbs. And we spoke a little bit before about the fact that snakes in the dark would be able to detect us wandering around in the pitch black because we're like little infrared light bulbs to a snake. And that's how some snakes catch their prey at nighttime. They don't need visible light to see. So because infrared interacts with matter so very commonly and so very easily, it makes sense to give a lesson over to just discussing it today. And that's what we're going to do. So if you remember the picture of what we had back on Tuesday, we can have absorption, we can have reflection, and we can have emission. And with infrared, not so much transmission because it tends to interact with the atoms. So not so much transmission. So let's just have a little look at how these things interact with objects. And we'll start off with some absorption. So what I've got over here for you is some bits of metal that I've just set up on a clamp stand, ready to interact with some infrared radiation. And then I have got myself some infrared radiation from a Bunsen burner flame. So what I'm going to do is put the Bunsen burner flame near to, but not directly on, the two bits of metal. And we're going to have a little look at how the infrared interacts with the metal. Now, if I show you the bits of metal again, you'll notice that I've painted one of them black. So they're both the same object. They're both a square of steel, that same thickness, same material. The only difference between the two is that one of them's just been spray painted. And the reason for doing that is because the main learning point from understanding about the interaction of the infrared with materials is that the infrared will interact with the very first atom that it encounters, which means that it doesn't actually matter what's inside an object. It's the surface atoms that the infrared is going to interact with. So yes, they're both steel plates, but that's actually irrelevant. What's more to the point is that one of them is covered in a layer of black paint and one of them is not. And it's the interaction with the black paint that's going to show us the difference in how it interacts with matter. It's a surface effect. Okay, so I'm just going to move the camera so that we can see what's going on. Okay, so I haven't moved the plates nearby yet. So what we're hoping to witness is a difference in how they interact. When I put those plates near to the infrared source, and there's infrared radiating out in all directions from this flame right now, what we're looking to see is there a difference in the interaction? And I'm hoping to see that one of the plates absorbs the infrared more easily than the other does. And so a simple way to test that, a really, really simple, straightforward way, is just to see which one warms up the quickest. And an even simpler way to detect that, rather than use a thermometer or something, is I've just got a little light object here. It's just a cork, like at the top of a bottle. It's really, really light. It doesn't really weigh anything. And I've just stuck a little bit of wax to the top of it. And you'll remember that wax melts really easily. And so we won't need to wait very long for this thing to get warm before the wax melts. And hopefully one of them will melt a bit faster than the other. So I'm just going to stick that one onto the black plate and stick this one onto the silvery plate. Same amount of wax, same cork, same separation, same size, everything's the same heat source. The only difference is going to be that one's black and one's not. Okay, so if I just move the camera for a second so you can see from above. So pretty much the same separation between the two plates. And all we're going to do now is sit and wait. And I'll just angle it down a bit because what we're waiting to see is one of those corks fall off onto the table. So I'll just make that slightly warmer. That happens a little bit faster. So it's a blue flame now, not really giving out as much visible light, but still giving out the infrared. So we're just going to sit and wait. But rather than literally sit and wait, because that would be slightly boring, we'll do a second experiment at the same time. So this object, similar thing, it's a steel cube, but it's hollow. So there's nothing inside it at the moment. And it's got a little hole in the top. And what I'm going to do in a second is pour some boiling water into that hole. And that's going to raise this cube up to, I don't know, 90, 95 degrees when the boiling water goes in, something like that. And like I've got two plates here, one black, one silvery, what we've done with this cube is paint the different sides of it. So there it is as it would be without any paint on it. It's just shiny steel, a kind of reflective color. And then I've got two sides which we're not really going to worry about too much because it turns out they didn't work very well. But this side here on the other side, this one is been spray painted black again, just like this one. So the difference between the two experiments is that this is hopefully showing heat or infrared being absorbed by the different materials. And because I'm going to put the heat inside this one, and heat it up, we're hopefully going to be able to detect a difference in infrared being emitted from the material. So you see that one as well? If I put that there, you can see that as well. So while we're just waiting for the corks to go, I've got a kettle full of water. I'll just boil it up so we get it as hot as we can. And then I'll pour the boiling water in, and we'll see if we can notice a difference between the infrared radiation coming out or not. At the moment, we have a little bit of melting going on. You can just see it's got a little bit shiny there. On that side, not so much. So it's looking a little bit like the black one's going first. It's kind of on a move. Is that what you were expecting at all? That the black one would go first? Down it goes. Silvery one, still in the same place that I put it at the beginning. Not going anywhere, but there goes the black one. So a really simple demonstration that a black surface is better at absorbing infrared radiation than a silvery surface. The black surface has warmed up quicker because it's absorbed the infrared radiation. And there goes the cork as the wax melts to demonstrate that. The silvery surface, rather than absorb the radiation, is really just reflecting it off, and the silvery surface isn't getting warm at all. There it goes. I think it's gonna fall off. Experiment over. Okay, let's get rid of that for a second. Bring this one into play. So the water's at 100 degrees, but the metal isn't. The metal's more at 20 degrees room temperature. And so the water's going to heat the metal up a little bit. So if you remember what we did a long time ago back in year 10 on specific heat capacity, a little bit of the energy from the hot water is going to be used to heat up the metal. And there's a lot more water than there is metal. So the water won't cool down that much while it warms up the metal, but we should probably expect them to meet at about 90 degrees, something like that. Just put a little lid on, stop it, stop the steam coming out. Okay, so this entire object is rapidly coming up to, it's probably already there, about 90 degrees, something like that. And certainly I can't keep my fingers on that. That is way too hot. And that is exactly the same on all the sides. I can't keep my finger on any of those sides. It's a single object. All four of the sides are all touching the boiling water inside. The boiling water is at about 90 degrees by now. The metal's at about 90 degrees. So the entire object genuinely is the same temperature. And it's really difficult to actually touch a thermometer against it to make it record that. So I haven't got a thermometer. But what I have got is one of these things, which, yeah, you've probably seen on the TV over the last year or so. You might even have one yourself. This is an infrared thermometer. So the idea is that I point that at something that I want to take the temperature of, and I press the little trigger, and the reading on the back tells me what temperature it is. So it is technically designed for people. So if I point it at me, reckons my temperature is 33.5, which to be fair is a little bit low. I probably wouldn't be very healthy at 33.5. So it's not great. Yeah.
That'll be your surface temperature. You got to put it on body if you want to get your actual internal temperature.
Yeah, that's what I did do. I just put it on my forehead.
Yeah, but they have a setting that'll, if you're 33.5 internally, I think you should be a bit more worried there, sir.
Yeah, but they're supposed to compensate, aren't they? They're supposed to give me a core temperature. But I've got one at home that does. This one.
Yeah, they've got it's 3 different modes. There'll be surface, body, and room.
It's a bit dumber than that. There is no mode button.
Oh, right, my bad.
I can change it to Fahrenheit if I want it. Anyway, the point is that it is absorbing infrared radiation through the front, and it's guesstimating the temperature on the back based upon the amount of infrared radiation coming out. So it kind of approximately got my temperature. So what we'll just shine it at is the dull black side. So I'll just pull the trigger and point it at this surface, and it's coming in at 86, 87 degrees, something like that. And that's probably a reasonable estimate of the temperature of the box. I poured 100-degree water in. It's warmed the box up a little bit, so it's cooled down a little bit. But yeah, it's probably around about right. However, if I now do exactly the same thing on the silvery side, coming in with the temperature at only 30, 35 degrees. What's that, 32? And the temperature of the silvery side is exactly the same as the temperature of the black side. It's just that the silvery side isn't allowing the infrared radiation to come out. The atoms in this black material, whatever the paint's made out of, the atoms are really, really, really excellent at vibrating at just the right frequency to release the infrared radiation. And so out the infrared radiation comes. And if I hover my hand near to that, I really can feel the heat streaming out of it. It's quite nice, actually. But if I spin it round, whatever atoms are in the silvery material, which will be different to the ones in the black paint, because black paint isn't the same as steel, different bonding, different atoms, whatever's going on with the atoms in this silvery surface, those atoms can't vibrate at the right frequency to emit the infrared radiation. And it's no coincidence that the infrared radiation is interacting with the surface similarly to the light. You can remember from the electromagnetic spectrum that infrared and visible light sit right next to each other on the spectrum. So we shouldn't be very surprised that the infrared and the visible light behave in a similar way. Right now, if we look at the black side, all the light in the room is being absorbed by that black side, and there is none coming back out, which means when we look at it, we don't see any light, and that's what we refer to as blackness. However, if I show you the silvery side, the light from the room is landing on the silvery side and reflecting straight back out into the camera. And you can see that there is light reflecting off it. In fact, you can probably see the camera a little bit. Oh, maybe not. It's a bit distorted, isn't it? So lots and lots of reflection of visible light, lots and lots of reflection of infrared as well. That's what we were seeing here with these things, that the infrared radiation was reflected off the silvery surface and couldn't get into it. Now what we're trying to establish an understanding of is that just like the light can't get into this surface, the light can't get out of the surface either. So there's a whole load of infrared trying to get out of this can, and it's succeeding very, very well from the black paint, streaming out of there. But there is no emission of infrared out of this silvery surface. So if I touch the surface, it's hot enough to burn me. I can't keep my finger on that. But just a couple of millimeters above the surface, there is no heat at all. I wouldn't even know that the can was there if I couldn't see it with my eyes. There's no sensation of heat in my fingers at all at the moment. Whereas if I put my hand just a couple of millimeters above the black surface, that's really very hot, and I don't want to keep my hand there for very long. So I need you to start thinking of surfaces as kind of, I don't know, like in an analogy, kind of like a doorway, and the light is entering the doorway if there's more on the outside than the inside, and it's leaving the doorway if there's more on the inside than the outside. So with these metal plates that we were putting near to the Bunsen burner, there's very, very little heat inside the metal plate. The atoms are only vibrating a little bit, and so they might be trying to radiate a little bit of infrared. But outside, there was a huge amount of infrared raining down on the surface. If you think of it as a building, think of it as like an office building at the start of a day when there's hardly anybody inside the building and all of the people coming to work are on the outside of the building. So they're all trying to get inside the building from the outside. There's more on the outside than there is on the inside. So you might get maybe one person trying to leave, but you might get 500 people trying to arrive. And so the net flow of the infrared, in this very stretched analogy, would be people entering the building. But it depends on the size of the doorway, right? If you've got some big office building with the tiny little doors in it that only one person can fit through at a time, then most of the people are going to arrive and not be able to get in because there's tiny little doors. Likewise, at the end of the day, when everybody's trying to go home, if there's only one door, they're all going to be queuing up inside the building and just a tiny little stream of people coming out of the building. That's kind of like the silver. It just doesn't let the infrared pass through it. If the heat's on the outside, it can't get in. And if the heat's on the inside, it can't get out. However, in my somewhat strained analogy, black surfaces are like buildings with massive doors. And so huge numbers of people can pass through it in either direction. People can arrive, people can leave. And that's what we saw with the infrared, that if you have a black surface, if the heat's on the outside, it can get in. And if the heat's on the inside, it can get out. Black surfaces interact really, really very well with infrared radiation. Silvery surfaces hardly interact with it at all. In fact, the infrared just generally reflects off. And that is what I wanted you to take from our discussion about infrared radiation and matter. However, what I've just shown you, those two demonstrations, are actually one of your 10 required practicals. Now, I know that the exams have been cancelled, but schools are still going to have to base your grades upon something. And although we've been giving you some tests, we haven't given you as many tests as we would have liked to. I mean, right now, you're supposed to be doing mock exams, but you're not. So in 6 weeks' time, when you're back in school, we are going to assess you. And so it's really important that you stay on top of the requirements of the specification, because those are what our assessments are going to be based on. So even though you're not going to get external exams, unless the government tells me to do anything differently, I am still going to assess you internally. And one of the things I could assess you on, just like a real exam, would be the required practicals. So this actually, what we just did today, is one of the required practicals. So what we're going to just do for the remainder of today's lesson is make sure that you've got a summary of it in your book. Now, I'm going to fill up that board with a summary of it, but that's going to take me a few minutes to do, and it's going to be a bit boring if you're just sitting there watching me. So why don't you have a go at making a start yourself, and then you can just fill in the gaps from what I write on the board as well. So yeah, make a start. There's 2 different experiments. I'm just going to divide the board into 2 and summarize both of them. And then I'll put a little note at the bottom to summarize the science, which is basically that infrared interacts really, really well with dull black surfaces, but not so well with shiny light colored surfaces. Okay, you make a start in your book and just glance to the screen every now and again to check you're writing similar things to me. Okay, so there's a summary of the first one. You don't have to do exactly the same as that. It'll be retained better by your brain if you make your own version of it. But as kind of an example of what you could write, I'll do one of the others as well. Do the other one as well. The metal cube that I filled with water actually has a name. It's called a Leslie cube, after the person that first did this demonstration, I guess. You don't need to know that it's called a Leslie cube. I'm just mentioning it because you might see it mentioned in revision guides or revision websites, or maybe on Bite Size or anything you watch like that, YouTube videos. So just don't be thrown by somebody talking about a Leslie cube. It's just a hollow metal cube. You don't need to remember the name. It's just so you recognize it if somebody uses it at you. Okay, so there's your summary of the emission one as well. So what I'm gonna do now is finish the me bit of the lesson. So I'll leave the meet running and I'll leave the board up, and in a second I'll step out the way so you can get back to copying it. When you have finished copying down what's on the board, what I'd like you to do is use the remaining time in this lesson, which is what, 20 minutes, something like that, to return to the chapter 13 questions that I posted to Classroom in yesterday's lesson. And whichever question, wherever you got up to, just carry on from there for another 20 minutes or so, or whatever time you've got left after you finish copying down what's on the board. And then that will kind of, when you finish those chapter 13 questions, just keep chipping away at them when you get a spare moment. There'll be other lessons that maybe finish 10 minutes early that you'll be able to do a little bit more then as well. When you finish those chapter 13 questions and these notes behind me, that's kind of the end of the electromagnetic spectrum-y bit of the topic. We're going to stick with light waves next week for the last little bit, but less of a reliance on waves and more just straightforwardly looking at how light behaves, a little bit like how we did reflection and refraction. Okay, so I'm going to stop talking now. The meet's going to carry on running. As soon as you finish copying down what's on the board, you don't need the meet anymore, so you can leave if you want to, but I'll still be here. If you get stuck, if you want to ask any questions, feel free to unmute and just ask them. But like I say, finish that and then the questions, please.